Hi, so in this video I want to talk about using custom sorts in Python. Because we often need to sort a collection of objects based on some custom sort order for those objects. Objects may or may not have a natural sort order, but even if they do, we may want to sort these objects based on a different sort order. Now Python provides us with a very highly efficient algorithm for sorting. It's called the tim sort, and basically it's based on both the merge sort and in the insertion sort. And I have a link to that specifically in the Jupyter notebook that's downloadable. Link is below. And basically this Python sort allows us to sort collections not only based on the natural ordering of the elements in the collection, assuming of course that there is one, but also based on a value that's derived from each element. And that's what I mean by using a custom sort. And so this is a very powerful thing that we have available in Python, and I often see it not being actually used. And I see people sometimes resorting to writing their own sort algorithms because they may or may not be aware or don't really know exactly how this key option works when we call the sorted function. Now, one of the really important aspects as well of the tim sort algorithm is that it is a stable algorithm. What this means is that the relative order of two elements that are considered equal will remain in the same relative order once the whole thing has been sorted. So this may be a little confusing at first, but let's take a look at an example. Suppose that we have these tuples over here, right? And we can make a list out of them. So we can do a list of tuples, T1, T2, T3, and T4. Now we're going to sort that list based on the natural ordering of these tuples. So what does it mean? What's the natural ordering of a tuple? Well, basically it's going to order based on the natural order of the first element. Then for elements that are equal in the first element, or for tuples, sorry, that are equal in the first element, it's going to base the sort order now based on the second element, and so on. Now, of course, this assumes that these elements have a natural sort order. In this case, they're integers, so they do. So we can very easily sort those. We just call the sorted function and we pass it L. So let's see now what S looks like. And you can see that we have 1, 2, 3, then 1, 2, 3, then 2, 3, 4, then 2, 3, 4. That kind of makes sense. But more importantly, which 1, 2, 3 is this? Is this 1, 2, 3 this third one? Is it T3 or is it T1? Same thing with this. Same thing with 2, 3, 4. Which one is it? Is it T2 or is it T4? Well, because the tim sort is a stable algorithm, the 1, 2, 3 and 1, 2, 3 and T1 and T3 are the same, right? They're equal from an equality perspective, but because it's stable, the ordering is going to remain the same. So you're guaranteed that this first element is going to be T1 because that came first in the list. Then T3 was equal to T1, but it was second in the list, so it's guaranteed to come next in the sorted result. So let's take a look at that. Let's actually just verify. We'll look at the ID of each T for T in S. So these are the IDs. And then we can compare that to the IDs that we had in the tuples in the original list. So for T in L. So you'll notice that this first element in the sorted result was T1. The second element in the sorted result was T3. And then the third element was T2, and the fourth element was T4. So this is what I mean by a stable sort. And the reason this is an important property of the tim sort is that it allows us to sort an iterable using multiple passes of the sort. And I'll come back to that point later, because that's again something that you can do in Python. Now, the sorted function allows us to specify a key function in the call to sorted. This key function allows us to assign a different value to each element in the iterable and have the iterable sorted by that value instead of the original element that was in the collection. The key function is simply a function that transforms each element in the iterable to another value we want to sort by. So it is always a function of one variable because it is going to take just the element in the list or in the sequence or in the iterable more generally that you are sorting. It's going to pass that element to this key function. The key function is going to return some value that is going to have a natural sort order, and the sort will be then performed based on that returned value, based on the sort order of that returned value. So again, this is quite easy to see. Let's go ahead and do a little example. So we'll do this list here, 1, 2, -1, let's say 3, -4, and 5. Now we can sort this using the natural sort order. So we can call sorted on L. And of course, as expected, we get the natural sort order, right? From the negative integers, then all the way up into the positive integers, from smallest to largest. But now, suppose that we want to sort by the magnitude of each element, the absolute value of each element, not by the actual value of the element. So I'm going to start off by creating a function, because it's going to be that's going to be our key. And it is a function that's going to take a single argument. In this case, my list is composed of integers, so I expect this argument is going to be, therefore, an integer. And I'm going to do it this way. And don't yell at me, I will come back and we'll write this better. But for now, I just want to show you that it's just an arbitrary function that can do whatever it wants. So here I'm saying, well, if x is less than 0, return -x. So for -4, it will return 4. And if it was positive, just return the number as is. And now we can do the sort based on this key. So we're going to sort L, but now we're going to specify the key, and we specify the function. We don't call the function here, we just specify the function that we want to use. That is going to get applied to each element of L, and the sort is going to be then based on the absolute value of the numbers. And so as you see, we get 1, -1, 2, 3, -4, 5. Now, of course, for the absolute value, we really don't need to define our own function, since Python already provides us, and actually provides us a few, like, for example, the built-in ABS function, but you also have some in the math library and so on. So instead of writing this custom function, we can use one of the built-in functions. That's absolutely fine. It's the ABS function. So we can achieve the same result this way. Now you can see that by default, the sort order is ascending. Now we can easily reverse that using the reverse argument of the sorted function. So let's go ahead and do that. We'll say sorted L, and then key equals absolute. So we'll do a sort based on a key, but we're also going to reverse the order, like so. And as you can see, now we get basically the same thing, but in reverse order. So I again want to just point out the stability of the sort, right? 1 and -1 both have the same absolute value, and they're smaller than all the other absolute values, so they come first. But they come in this particular order, 1 and then -1. Well, if we look back at what our original sequence was, we had 1 followed by -1. So you can see that it kept the sort order, right, in both these examples. Now, if you look at this one, this result here, that's not quite the same as reversing this list that came as a result of calling sorted. If you see the 1 and the -1, if you were to reverse this over here, you wouldn't get exactly the same thing. Let's go ahead and just put them side by side, and let's just reverse. Let's do it this way. Then you can see that here, -1 would come before 1. Well, when we did the stable sort in this direction, it was 1 and then -1 because that was the order in the list. Now, when we are sorting in reverse direction, well, the 1 came before -1 in the original list L, so that is still maintained. So that's not quite the same thing, right? Doing this and doing this is not the same, doesn't give you the same result because of the stability of the sort. Now, this key argument can be very powerful. One module that is very helpful in this context is the operator module, and I provide a link to the Python documentation for the operator module in the notebook that you can download. So that module provides us a functional approach to many operators. In particular, we're going to make use of the attrgetter and itemgetter functions. Those are the two that I want to call out in particular. So let's look at those. and let's look at the attribute getter one first. So from operator, we're going to import attrgetter. And then suppose that we have class defined this way. So from math, I'm going to import distance, and we're going to create a class point, and that's going to take in basically two parameters. So def will do the init, self, and then we're going to pass in the x and y. So this is a point in two-dimensional coordinates, and we'll use self.x equals x and self.y equals y. Now I'm going to define a property here called the quadrant. And the quadrant, basically, if you look at your xy axes, you start your quadrant number 1 at the top right? So where x is positive and y is positive. Then quadrant number 2 is, as you go anti-clockwise, you get quadrant number 2, and then you'll get quadrant number 3, and then quadrant number 4, which is just below 1. So let's go ahead and do this. I'm going to define it as a property. So we'll do quadrant, and we just need self. This is a method. Well, actually it's a property, but of course written as a method. And we're just going to basically classify. I'm going to do it this way. There's probably easier or better ways to do it, but I'm just going to do it using just a bunch of if statements. So if that's the case, so if x is greater than 0 and y is greater than 0, we'll return y. Otherwise, if y was not greater than 0, then we're in quadrant number 4. And then we'll do an else. So now x is negative. And of course, we now have to again differentiate whether y is positive or not. And if that's the case, we'll return second quadrant. Otherwise, we'll return the third quadrant. And if we're at the origin, I'm just going to return 0 in this case. I'm going to say that it's the 0 quadrant when x and y are both 0. Okay, so that's the quadrant defined. Now let's go ahead and create the absolute value. So we're going to implement an absolute value so we can call the ABS function basically on our point. And for that, I'm going to use the math distance. So I'm going to return the distance, and it needs two tuples, 0, 0. So the distance to the origin, and then self.x and self.y. So basically we're looking at the Euclidean distance between the point and the origin. And then lastly, I'm going to create a wrapper for this. So this will be our string representation, and we'll use an f string, and we'll say point. And then in here, we're going to say self.x, comma self.y. And that needs to be in curly braces as well. We want to interpolate that. And then I'm also going to add a little bit more. I'm going to say magnitude equals, and then we're going to call the absolute function on self. Now we know that it's going to call this function, so that's going to work. And the only thing is I want to give it some formatting, since that's going to be a float, and we'll do, let's say, 3 digits after the decimal point. And then I also want to specify the quadrant here. So I will say quadrant equals self.quadrant. All right, so that's going to be our wrapper for this thing. So let's make sure it works. Let's go ahead and create a point. And we'll do -1, -1. So we know that that should be square root of 2 from the origin, right? So if you see, we have the point -1, -1. Magnitude is 1.414, square root of 2, and it's in quadrant number 3 because x is negative and y is negative. So we're in quadrant number 3. Okay, so that's our point class, and let's go ahead now and create a collection of these points. I'm just going to copy paste that from the notebook. So here I'm just creating a tuple with various points in that tuple. Now each of those points have a distance from the origin. We can just call absolute value of p for p in points, like so. And you can see they all have some kind of distance from the origin. And they also belong to some quadrant. We can say p.quadrant for p in points, like so. And you can see that each point is in some specific quadrant. Now, we already know how to sort by the distance from the origin. We just did it, right? We used sorted. And then we're going to sort our points, and then we're going to specify our key to be the absolute function. And that's going to basically call this function here, and it's going to therefore use the distance from the origin as our key. So it's going to sort these points based on these values over here. And as you can see, indeed, the magnitude here is increasing from smallest magnitude to largest magnitude. Now again, we are going to have a stable sort. So for example, these two over here have the same magnitude, 2, 2 and negative 2, 2. So if we go back, you can see that 2, 2 came before negative 2, 2, so it stayed in that same relative order in our sorted result. But now, what if we want to sort by the quadrant instead? Well, we need to provide a key function that will return the quadrant for each point. Now we can do this by defining our own function that will receive a point as the argument and return the quadrant of the point. So we can definitely do it this way. Sorted points, and then key equals, and we're going to just create another function. And here I'll just do a lambda function. And it's going to take a point, it's going to receive a point as an argument, and it's going to basically return the quadrant of that particular point. And so when we do this, you can see that indeed we now have a sort based on the quadrant, from lowest quadrant to highest quadrant. But even simpler than creating a lambda function is to use the attrgetter function that we just imported from the operator module. Basically, this function returns a new function that will get the named attribute of whatever object gets passed to it. So this is very similar to the getAttribute, the getAdder function. Let's go back and let's just take a look at that function quickly. That's a built-in function to Python. So we can get an attribute. We can certainly say p.quadrant, right? That's one way of getting it. But here what's happening is we're typing the name as part of our code. What happens if this name comes back maybe as a string from someplace else? Maybe the user typed it in or it came back from another function. Well, in that case, you can get the same thing by calling this getAdder function, and then you pass it the object that you want to get the attribute on, and then you pass it a string that contains the name of the attribute. So this is no longer code, this is just a constant string. And when we do that, we get the same thing. We get basically p.quadrant, which was 1. And so the attrgetter function works practically in the same way. So let's go ahead and define this quadrant, getQuadrant equals attrgetter, and then we'll pass it this name here, quadrant. And I got to spell it right. Now, what does attrgetter return? Remember I said it returns a function. In fact, if we now look at that function, you can see that it is not a value, right? It's just this attrgetter function. And we can now call this saying getQuadrant, and then we'll pass it just the point p. So you'll notice that basically before, in order to get the quadrant, I had to do p.quadrant. Here, I'm just calling a function that takes in the point, and it's going to return the quadrant. This is very similar to using the lambda, basically. It's just that the syntax is a little cleaner. So it's the same thing as doing this, basically. Just like we had before. Now I can call fp. But you can do it this way by using this attrgetter function, by using this over here. So now that we know that, let's go ahead and do the sort again. So we'll say sorted, we have points, and then the key now is going to be what? It's going to be attrgetter quadrant, like so. And so we get the same result as before. It's just that this is slightly cleaner syntax. So this is cleaner syntax, but let's also do some quick timings to determine which retrieval is faster, using attrgetter like we did here, or using the user-defined function, the lambda essentially that we used, right, in the other example. Let's just go back and let me copy paste that, this one, right? So we have basically these two options. Which one is faster? Well, let's go ahead and do some timings. So from timeIt, we're going to import timeIt, And then I'm going to create a point, p equals point, let's say, and that's point. Let's do -2, 1. Then I'm going to create this function using attrgetter. And we're going to pass it the string quadrant. So I'm creating this function. I'm going to then say result_1 equals time it. And we're going to call func on p. So right now I'm not looking at sorting. I'm just looking at which is faster, using the lambda or using the attribute getter. So we're just going to call that basically get the quadrant for p, and we're going to pass it our globals. So globals equals globals, and then we'll do this, let's say 10 million times. Then the next thing I'm going to do is the same thing, but now using the lambda. So I'm going to say lambda p, and we're going to say p dot quadrant. And then we'll say result_2 equals time it. And now we'll just do func p again. So actually, let me just copy paste this. We're doing exactly the same thing. And then let's go ahead and print the results out. And let's call this result2. Then I'll print the results out. So we're going to want to print, and let's do an f string, and we'll say result_1, and we'll do that to 3 decimal points, and then we'll do the same thing with result2. Okay, so now let's run this. As you can see, the attribute getter was actually a little bit faster, and it's pretty consistent. Is actually a little faster than using the lambda. So it's more readable, and it's actually a little bit faster. I wouldn't worry about, the speed here is really not that much, considering that we did 10 million iterations, but still it's there. Next, suppose we want to sort our points tuple this way. We want to sort by quadrant ascending, and then by distance from origin descending. Now, since the Tim sort is a stable sort, we could actually do this in 2 steps. And it's a pretty common way of doing kind of these complex multi-step sorts. Doing it this way by applying one sort after another. You could write a pretty complex key function to do the same thing, but usually you'll end up with cleaner code. And then we'll take a look at timings also on doing that versus the more complicated key function. So let's go ahead and do that. So let's call it sort1. So we're going to say sorted points. So remember, we want to do the sort, first of all, based on the quadrant. So let me actually put this in here, just so we have this, so you can see that. It's in the notebook, right? So we want to sort by quadrant ascending, and then by distance from origin descending. So by absolute value descending. So the trick here is we're going to sort by the distance from the origin descending first. The reason we do that is because now we're going to end up with a list that has all the points sorted by distance. And then we're going to sort by quadrant. But because it's a stable sort, the order of the points relative to each other for equal distances is going to remain the same. For equal quadrants, is going to remain the same. So let me repeat that. We're going to first of all do our sort this way. So let's go ahead and actually let's do the sort. Let's see what we have. So now we have these points, and they're sorted in reverse order based on the magnitude. Now I'm going to sort by quadrant. Well, a lot of those points are in the same quadrant. But because I want my sort to be by quadrant ascending and then within each quadrant by distance descending, well, since I already have a descending here, when I do the sort by quadrant, these 2 points are in the same quadrant, so they're going to end up at the beginning of the sort, but in which order? Well, it's a stable sort. So the magnitude, this point is going to come before this one. So the magnitude is going to be greater than this one. So let's go ahead and actually do that. Let's call it final sort equals sorted. Now, I have to pass it sort1, not the original list. I now have to pass it this intermediate list that I created. And I'm going to use the attrgetter function. And we're going to say I want to sort by quadrant now. And let's see what the result is. Let's close this, and then let's see what the final sort is. So as you can see, now we have things sorted by quadrant, right? Ascending. But if you look within each quadrant, we have the magnitude descending. Same thing here. And that's because we took advantage of this stable sort. So that's something that's really important to understand in Python and understand how stable sorts can help us do more complex things. Now, of course, you can also do this sort in a single step by using a more complex key function. Let's go ahead and write this key function. So we'll say sort by quad and magnitude. And then this is going to take in a point object. And it's going to basically return a tuple. And we're going to return the quadrant. And now, so we're going to sort, what's the default? Ascending by quadrant. But we want to sort in reverse by magnitude. Well, if I just put in the magnitude here, that's not going to help me. So what I need to do is I need to put, let's say, a negative sign in front of the magnitude. So I'm going to sort now by these tuples. And that's going to give me the same effect. So now I could say sorted points, and then we'll say key equals sort by quad mag, like so. And then we'll get essentially the same result, right? You can see that we have the same sort ordering. Now, you may be wondering about the performance impact of sorting in 2 steps versus using a more complex and less readable, therefore, key function like we had here. Now, there is one thing though. If you think about this, this is not creating extra lists. So there is a memory requirement, then additional memory requirement when you do those sorts using multiple steps that you do not incur when you do a single step. But what about timings? Is one faster than the other? Well, let's go ahead and try that out. So basically, I want to test these 2 scenarios, right? This is the first one where we have this temp list. So we're incurring the memory cost of creating a new list. And then we have the final sort. So we're doing a 2-step sort here versus doing the single-step sort that we had over here. We don't incur a copy of that list like we had here with the temp list. Okay, so these are the 2 things that we want to test. So again, let's do some timings. So here I'm going to say from random, I'm going to need to import randint, and we're going to import seed as well. And then we're going to create a list of 10,000 points. So I'm going to set the seed just so that we have repeatability. And then points equals, and I'm going to use this. I'm going to use a point. I'm going to use the randint function. I'm going to create a point with the x coordinate somewhere between 1,000 and 1,000. And then the y coordinate is going to be exactly the same thing. It's going to be a random integer between -1,000 and 1,000, like so. And we're going to create how many points? We're going to say for that in range, and let's do 10,000 points. Okay, so this is a list of 10,000 points. And we're going to use these 2 variants of the sort that I showed you over here. So what I'm going to do is I'm actually going to do it this way. So what I'm doing is instead of having a temporary variable to store that sorted thing, I'm going to pass it directly to another sorted function. So I've got the 2 sorts happening, right? In the first sort, we're doing the absolute sort reversed, and then in the second sort, we're going to sort by quadrant. And I'm just doing this so that I can easily call this when we do the timings. So these are the 2 that we're going to do. And you know, as a sanity check, you could make sure that those 2 sorted values, those 2 sorted results are actually equal. And of course, it's true. Okay, so now let's time it. So key func equals attrgetter. And again, I'm going to create my key func outside. I'm not going to redefine it each time here because I just want to time the sorting piece. If I was to sort, if I was to time this precisely, I would also be, timing how long does it take to create this function every time. But that's not reasonable, because if you're going to sort this thing, let's say, then you're going to create your attribute getter function once and then run the sort, right? You're not going to run that attribute getter, a million times. So I want to take that out of the equation, so we're not timing something that's not actually relevant. Okay, and matter of fact, just to save some typing, I'm going to put this in. So here, what are we doing? We're doing this time it of basically this over here. And we're going to time this by running this 1,000 times. So I'm not incurring, right, the cost of creating this key function 1,000 times. And then we're going to do the same thing, but now using the more complex key, which we have already defined, right? So it's this lambda over here. And then we're going to print the results out. So let's go ahead and do that. And let's run this. And I'll pause the recording and come back once it's finished. All right, and as you can see, using the double sort came out to be faster than using the more complex key function. So are you surprised? I mean, I was. The first time I came across this, I was quite surprised. And the only thing I can think of is that timsort is very efficient if the data is already partially ordered. Well, and it kind of is, since we stacked one sort after another. The first sort kind of already partially ordered things for the quadrants, right? So I think this is what's happening. Now, if you know different, please let me know. Let us know in the comments, because I'm really curious about this, because I was really surprised the first time I saw that. Now, in general, however, do not rely on one approach always executing faster than the other. If the sorts are a potential bottleneck in your app, try both methods. See which one actually performs better with your particular data. That's really important. Now, of course, as I mentioned, there's a memory trade-off between the two approaches, right? In the stacked approach, we're essentially creating an extra list, right? In this case, just one, because we had these two sorts. But you can think that if you had, let's say, if you were stacking 3 or 4 sorts, well, you'd be incurring, 2 or 3 extra lists that would have to hold all the elements that you're sorting. If the elements that you're sorting are not huge, if there's not a huge number of them, maybe that's not an issue. If there's a lot of them, maybe that is an issue. So the next function now that I want to switch to in the operator module was the itemgetter function. And basically it's a function that returns, again, another function that retrieves an item from a sequence by index. So let's take a look at it. Let's say from operator, we're going to import itemgetter. And let's just say get item 2. Let's go ahead and create this new function. Get item 2 is itemgetter with index 2. So get item 2 is a function that we can call, and we can basically pass it any kind of sequence, anything that's indexable. So here I'll just pass it a string. And it's going to return which one? It's going to return the element of this sequence at index 2. So it should return C. And indeed, that's what we get. So again, this is something that helps us when we're using the sorted function and specifying a key. Instead of having to define a custom lambda that's going to take the element and then return the element at index 2, you can do that without creating a lambda, just using the item getter. So let's go ahead and test this out. I'm going to copy paste this example from the notebook. So let's say we have all these strings and we want to sort based on the second character of each string. Now again, we can use a lambda for that. Nothing wrong with that. We can say key equals lambda SS1, like so. So we're basing our sort based on the second character, and we're using a lambda function. And of course, now we get that result, PDQ, CGI, etc. But we can also use the itemgetter function, like so. L and then key equals itemgetter, key equals itemgetter 1, like so. And as you can see, we get the same result. Now again, it's worth looking at the performance difference between the two approaches. So again, just to save typing, I'm going to just paste that in from the notebook. So we're going to test how long it takes to call sorted with this key function that we define using a lambda, and we'll do it 10 million times. So that took 4.6 seconds. Now let's do the same thing, but with itemgetter. And that's 3.56. So as you can see, just like before when we were using the attrgetter, the itemgetter seems to be faster than using a user-defined function. And in my opinion, and more importantly, I think this kind of code is more readable than this one. This is very easy because we know what itemgetter does. Here I've got to read a lambda function to figure out, oh, okay, well, it's doing this. Or it could be a function that's defined elsewhere, and I got to go look it up and see what it's doing. And then same thing with the attrgetter as well. So as usual, you have a number of options available to you when sorting. But before you decide on always using a specific pattern because you think it's more performant, take a minute to determine if the sort is going to be a bottleneck in your application. And make certain, don't just guess, because guessing is bad, right? Very often we have a gut feel for, well, this is where probably our code is the slowest in our app, and we get it wrong. I've seen that, and I've done it many times. So over the years, I've learned not to make those kinds of assumptions. So make sure you know for sure where your bottlenecks are, then start doing your optimizations. In the meantime, when you start writing your code, go for readability. Go for the most idiomatic Python that you can write. I prefer itemgetter over the lambda, and I prefer the attribute getter over the lambda as well in terms of readability. All right, thanks for watching.